for travel demand modeling, and then realized that there's a lot more functionality and a lot more uses outside of travel demand modeling for land use and land use modeling. So we brought in Dr. Nagini Allura to kind of work out how we were going to do this and potential applications. And we started with one place, and then I threw a whole bunch of curveballs at Dr. Allura, and I think we've ended up with a really good project. So I look forward to kind of your overview today. Dr. Allura, thank you for your time and your staff's time on this. I think it's a really good product.
Thanks, Thomas, for the introduction. And also, we really appreciate working with the DOT on this one. Thomas and Vladimir and several others have been very involved in giving us feedback. So this is effectively the data products that we created. So I'll go ahead and start again for everybody's. We are recording this webinar so that we can have this documented for future, for those who could not attend and in future as a future reference. So this is the quick outline of my presentation and the webinar. So my objective here is not to completely talk about all the details of the project, because again, that alone could take a couple of hours. So our objective is to give you an introduction of what we did, what was the objective, what methods we used. We'll give you a flavor of the methods and briefly go over some of the findings, but then also show you the data product. So my PhD student Lauren will actually take the data, open that up, and show some of these examples that we can use it for, visually demonstrate what the data is, how does it look like. Once the DOT will let everyone have access, you can work with this, but we're going to talk about those aspects also so that we can demonstrate how to use it for various jurisdictions, and then some other potential use cases that might come up as we go forward. So again, for everybody, it is not new. Florida is a fast-growing state. We know there are changes happening on a yearly, monthly frequency on transportation, housing, mobility, demand, and also land use patterns that are evolving. So the current project is for all of those people who are working with the travel demand models. You all know about the FSU-TMS framework. This is a standard that Florida Central Office has supported and built, that is taken up by local jurisdictions, either use it directly or build on top of that. So that way, every jurisdiction in Florida already has access to some resources in the travel demand modeling regime. So we are thinking of this project as analogous to that, but in the land use, socio-demographics, and economic indicator space. So we want to build something that is available as a standard for everybody in the state. And then once that standard exists, local resources can be used depending on how much resources they have, either to use it as it is or overlay this with additional details specific to the jurisdiction. So if you're a city which has resources to have a land use planner, transportation planner, and you want to build more custom details in your model, you don't have to start from scratch. You can use the standardized model that we're building and incorporate that and build on top of that. Now, if you're a jurisdiction that does not have any resources to build your own land use model, you can take this. All you need to do is determine your study area. The data for the entire state will be available. This is the data products that we are providing. You can build your own model. We think that is a very useful tool for agencies to complement their existing travel demand modeling analytics with a land use, socioeconomic, and economic indicator model. So with the broad idea there, our objectives are, we want to establish, okay, there are a lot of socio-demographic variables, land use variables, and economic indicators that we can consider. We wanted to identify a universal set that are, again, useful, currently being used in travel demand models, and are also publicly available. Again, we don't want to provide a tool where we are using proprietary tools, and every time you use it, you have to pay a license. So what we're trying to do is generate indicators that can be produced from publicly available sources, the Census, American Bureau, and we'll talk about these data sources as we go forward. So that is one of the objectives. Then once we created the list of variables we want to generate, we wanted to develop an algorithm to generate these variables. Then we validated that algorithm, and using that algorithm, we generated the different variables in 5-year increments from 2025 through 2050. So for these 5-year intervals, we are doing this so well into the future. And our objective was to generate these variables at different spatial resolutions. So local jurisdictions and statewide models can utilize them. So we have block group, census tract, and county as the resolutions for producing output. So every variable that we generated can be utilized in those resolutions as appropriate. This is a broad overview of the process. So the research was executed in this fashion. We started with a review and a stakeholder survey. So where we looked at different land use models in the literature. Again, there is a whole swath of models that are existing, that are available. And we also conducted a stakeholder survey accompanying this literature review, where we reached out to different stakeholders. Again, some of you might have answered that survey there. We're asking, what are the important variables? What is the most important variable that you think is needed within this framework? And we got from that a list of variables that were considered important, and that allowed us to come up with a universal template. We looked at those variables demanded from the stakeholders and looked at, okay, which of these can be generated from an open source public software, public databases. And then we created that. Once we created that, we started processing the data. One of the major goals of this project was to use parcel level data for the entire state of Florida. As anybody who worked with parcel data would be aware, when you're looking at that size of parcels, there's huge processing and compilation tasks. So one of the things we had to do was make sure we are able to get all the parcels over several years available, so that we can start looking at parcel changes. So when a parcel is currently a vacant residential parcel, it changes to a single family residential. That is a change. So it can happen over a year or 2 years. So we need to identify, look at the different parcels and look at their nature of land use over time, and use that to determine whether a parcel has changed or not. All of that work went into in the data compilation and processing stage. Then, along with the data processing, we developed a framework of how we can build this algorithm, that is using openly available sources of data to build a evolution framework, if you will, of how land use patterns, economic indicators, and socioeconomic variables change over time. Once we created the conceptual framework with the different components, the next stage was using the data to estimate the different components. So for example, if you have a parcel, we need to understand when and how will that parcel change. So that requires a model. We built a model for that. If the model decision is to change, what does that change into? So it's currently agriculture. Is it becoming single family, or is it becoming retail establishment? So things like, so we had to develop models for all of these choices. Once we were able to estimate all of these models and run through them and check them, the next step was building the software. So where we used open source Python software that allows us to run through parcels for a base year. So run through all the parcels in 2020 and determine what happens for 2021, and then evolve that over time. Because we are trying to get to 2050, we are looking at parcel level changes over time for up to 30 years. So we did that. And then once we get the outputs, again, we do this at various stages. Even in data processing, we wanted to make sure, okay, our data sets, again, these are large data sets. So we're trying to ensure there is consistency in the data by looking at aggregate trends and regional trends as appropriate. Same thing with the outputs. We did a lot of validation and consistency checks to make sure that the results we are predicting are reasonable and make sense. Again, I think at this point, it's important to also note that while we are using parcel level data, the objective is not to suggest outputs from this project are not to suggest that this is how land use should happen in the future. What we are trying to suggest is, given how things are evolving, this is a potential cross-sectional view of land use patterns over time. Given we are using parcel level records, we will have variation if you change the seed. So if you change the random seed and run the software again, it will give you different output. So we don't want to focus only on a single parcel and say this is what our prediction is, but our objective is to get a little more aggregate level data. So at the census block group, at the county, at the census tract, by aggregating this into that resolution, we will be able to have more stable results because we are modeling at a parcel level. That's the objective and thought process behind this. So I'll go over main details of some of these tasks. So I'll start with the data preparation. So the data preparation started with collecting data for 2011 to 2020 from different publicly available sources. We used U.S. Bureau of Census Bureau, American Community Survey, Bureau of Economic Analysis, Florida Department of Revenue for the parcel data, again FEMA to identify flood zones and water parcels and so on. Also the roadway characteristics inventory from DOT. So all of these are again are available to all of you. So these are the sources that we used. Uh, we the biggest challenge in the data processing is mainly pertains to the parcel level data, because there is a large number of data, and when things change, we have to match the parcels from one year to the next year to determine whether things have changed or not, and then identify that and tag that. So we process that. Then once we have data at the parcel level processed, we can aggregate that to a block group. We can aggregate that to a block group, census tract, and county, and use those indicators. So for example, if we wanted in a model to look at the percentage area which is single family in a block group, again, we use the parcels to aggregate that to that block group, and that becomes an independent variable in one of the models. So we were able to interoperate between levels, so we can go from block group to census tract to county as appropriate as needed. Again, these are some of the data sources paired with the variables that we are using. So population, for example, came from Census Bureau and ACS, households, ethnicity distribution, vehicle ownership, median income, and number of business centers. Again, I think everybody will be aware of these variables. I'm not going to spend too much time on this. So if you look at Bureau of Economic Analysis, here is where we looked at data on the number of jobs and on the number of jobs by industry. We used the FEMA databases to get the flood risk level information in our models. So in terms of the spatial resolution, again, we tried to obtain data at the lowest possible spatial resolution, the finest possible spatial resolution, because we can always aggregate it very easily. But for some data sources, they were not available at, for example, for number of jobs, we could not get it at a block group resolution. Same thing with median income, we could not get it at the block group. So, but median income, we do it at the census tract level, and number of jobs we do at the county level. So these are some of the trade-offs that we had to make based on data availability and information that was available to us as we modeled. So parcel level land use was only used for parcel decisions and their changes, but everything else was either at the block group, census tract, or county. So this is again a quick summary of some of the data that we processed. So this is land use distribution. Again, you'll see this is by area. So not surprisingly, in Florida, we have a large percentage of data which is agriculture. Everything else is less than 15%, but agriculture goes up to 44%. But when you come to parcels by count, again, not surprisingly, you have a large number of single family residential units. It goes up to 60%. Everything else is under 15 or 16%. Again, we also generated a number of charts. I won't go into all of these. Again, just to make sure our data represents what we would expect, you'll see a lot of, this is the population density. You can see most of the urban regions have higher densities here as you would expect. Again, agricultural land percentage. Again, this mirrors the other one. So you'll see a lot of agricultural land in areas where there's less population. Industrial land percentages again are slightly low on the lower side, but you'll see again pockets of industrial activity around the urban regions. Similarly, single family residential percentage, different land use mixes. Again, all of these are generated to illustrate how the data we have processed represent reality. So we wanted to look at these at a higher to find any significant errors that might have crept into the data generation process, if any. We also undertook data consistency analysis. I think this is based on some of the comments from Thomas and several others who were looking at it, where we looked at, okay, how does the population versus per household ratio look like, jobs versus jobs per household, a number of residential parcels, and different areas per household, and so on. So again, these numbers were generated to reflect reality, and they represent what you would expect from a state like Florida. These are the representation of that, where we have residential parcel density. Again, as you'll see, the higher density you'll see around the major urban regions in the state. The next step and the important component of what we did was a conceptual framework for land use evolution. Again, there have been several land use models that employ different approaches. So here we used uh, an approach where we are looking at simulating what happens every year. What we did was we have a land use model that looks at each parcel and looks at, okay, what will happen in this year? Will this parcel change or not? And if the parcel doesn't change, there's nothing to do. If the parcel changes, we need to figure out how much of the parcel changes and into what land use type that parcel will change into. Now, when this happens, across the state, things change at the aggregate level. So it's not just single parcel, that multiple single family homes come into existence. So that might change transportation needs, that might increase transportation mobility, that might affect economic indicators, it might affect the population in the region and in the surrounding region. So there is an interaction across the three components: land use, socioeconomics, and economic activity. So we wanted to capture that. So to do that, everything at the parcel level is aggregated to the higher level zones, and they influence the other two characteristics. So parcel land use influences socio-demographic, socio-demographics influences and influences economic indicators. So once we have outputs for 1 year, both socioeconomics and economic indicators influence the next year of land use. So this is an iterative process where all of these three work together to bring about changes, again, which is what to represent what happens in the real world. So we did some aspects of compiling all the data in a data store, and we also use controls. What I mean by that is we are not really researching socio-demographic changes, because again, that in itself can be a multi-year project. So we are using data that has been established by University of Florida Demographic Center, and that has been validated, and that has been in use for several years. So we take those data as controls. So we use that to make sure we match our population changes to that. So for example, if you predict a change of 13%, but if the change in that 5-year period is only 12%, we scale it down to make sure we are not overshooting those numbers. So that's the kind of controls we use to make sure we are not going beyond the expected norm at the very high aggregate level. So that way we ensure that the simulation does not run out of bounds in that way. So this cycle runs every year. So even though we are doing outputs every 5 years, in our software, when we finalize this, it runs every year. We take out the outputs every 5 years and save them and keep continuing into the future. So this is the model framework for the land use. So we have inputs that come from land use, demographics, and economic variables. We have the existing land use parcels. And then these parcels undergo a change if those parcels are changing. If not, they remain the same. And then we update the parcel data with the land use patterns. And then we keep this cycle moving forward so that every year things change. So within the land use model, we are following a specific structure. The first choice for every parcel is, will you change? So the parcel might change or not change. So if it does not change, there's nothing to do. We just keep that parcel and copy it to the next year. If it changes, then we have to think about several aspects. So we have noticed in our data, in our parcel conversions, that when a parcel changes, it's not necessary that the entire parcel changes. So it could be a 50-acre agricultural parcel. So a developer might purchase the whole thing, but only decide to build on 10 acres. So that would be a partial conversion. So one of the decisions we added when we look at a changed parcel is, will it be a full conversion or a partial conversion? If it happens to be a full conversion, it's straightforward. You're saying this parcel is fully converting. We just need to figure out into what. So there's a model for that. If it's a partial conversion, we need to figure out how much of the parcel is converting. So let's say 30% of the parcel is changing. Then that 30% goes back to this module where we try to figure out, okay, 70% remains the same. The 30% changes. What does it change into? Again, the same model can be applied to figure that out. So if it's a full conversion, you'll only have single parcel. So single parcel that was vacant residential became a single parcel, single family. But if it's a partial conversion, half of that or 70% of that remains agriculture, only the 30% changes. So we track that. We keep that. Okay, now that single parcel became two parcels. One is existing parcel and the other is the new land use type. So this is captured in our change process. Again, if I remember correctly, about I think full conversions are the majority, but we did have enough partial conversions to warrant this careful analysis in the land use pattern. So this process continues by land use type. So for each land use type, the current land use type parcel, we run this. So if you have a single family parcel, there's a whole suite of models just for single family. Multifamily, there is another one. Agriculture, there is another one. Industry. So all of these are run separately for that group of parcels, because what parcel you start off has an impact on what you change into. So we could not just do one model for all land use types. So we had to create. So we ended up creating 14 systems of different parcels which had reasonable share in the overall sample structure. For socio-demographic and economic development variables, again, I showed this briefly there. So these are the variables that we are generating: the population, households, vehicle ownership, and ethnicity distribution for the socio-demographic side. For economic development variables, we are looking at number of jobs, the jobs by industry, number of businesses, and median income. So again, the next slides is the detailed processes for the socio-demographic variables. So we look at population. What we did for population is we modeled the change in population. We are not modeling the whole population every year. What we are trying to figure out is it changing by 3%, 2%, or minus 1%? So that way, we are not having a jump of unexpected. So if you have a linear regression modeling the total population only, when you predict like this in a simulation setting, it could happen that you have 8,000 one year, 12,000 another year, 8,000 again in the next year. So we did not want it to be noisy like that. So by looking at the percentage change, we're trying to keep it closer to what it was previously, which is more reasonable in how it works. We modeled this at the block group. We used economic factors, demographic factors, and land use factors at the previous year to influence this process. Same thing with number of households, vehicle ownership, and ethnicity distribution. Vehicle ownership and ethnicity distribution were modeled as fractions, where we are looking at percentage of households with that share. So 0, 1, 2, 3. So what is the share of households with 0 vehicles, 1 vehicle, and so on? So because of the fractional nature, we developed what is called a multinomial logit fractional split model. Same thing for ethnicity distribution, because these are fractions of people of different ethnicities. We employed a fractional split model. Now, coming to the economic development variables, we model number of jobs, jobs by industry. So given the total number of jobs, we also wanted to figure out jobs by industry. So if we model fractions, if you know the total, you just multiply the total with the fraction, you get the number of jobs by industry. Similarly, number of businesses and median income. These are the various factors. So for number of businesses, we did not do a model. We actually used a conversion factor based on number of jobs. So we were able to look at some data to get how many jobs are there on average exist within each business, and we use that to convert. So once the number of jobs was determined, number of businesses was automatically came from that. So here I will quickly go through one model system to illustrate how we did this. Again, the final report will have all the details of all the models, all the different variables that we estimated, and so on. And again, I'll be happy to discuss these in detail with you if you want to discuss these later. But for the interest of the time, I'm only going to talk about one of them. So here I'm going to talk about single family. So what we did is, the first step that we looked at is whether a single family parcel will change its land use or not. So again, we have different variables. We notice that percentage of 0 vehicle households, presence of multifamily, again, flood zone. These are different variables that tend to influence whether it changes or not. So this gives you a probability. For every parcel, this model gives us a probability for change. So that is what is used as an input in our simulation to determine, well, whether that parcel will change or not. Now, for those that are selected to change, there is another binary logit model to determine whether it will be a partial conversion or a full conversion. So here, base is the partial conversion. If you have a positive utility, you're more likely to do for a full conversion. So you'll see that, again, mixed use parcels are likely to change into higher mixed use percentages, increases full conversion. Similarly, there is information that there's a population density increases, the conversion is more likely to be partial. Again, all of these are variables that influence single family parcel conversions in this one. Then we looked at area, the number of the proportion of area that will change. So we are looking at two fractions, no change fraction and the change fraction. So we are modeling that based on this. So if you have high mixed use, then large fractions change. We have that here. So these variables determine whether 70% of the parcel will change, or only 20% will change, or only 10% will change. This is the output from this model. Then we have the new land use type model. This is where we will model what will the single family change to. So because this is a single family parcel, everything else are the options here. You'll see vacant residential, multifamily residential, recreational, public, agriculture, and so on. And you'll see a low share categories. So we have used 14 land use types in our overall system. But for any land use, when you're converting, some of the land uses are very small shares. So we're talking about less than 1%, less than 0.5%, and so on. So all of these categories are grouped into one low share category alternative. And if things go into that alternative, we will allocate the percentage based on what we have in the observed data to be that parcel. So that's how we determine which parcel changes into what. And this is the model. Again, you'll notice we're using variables at the Brock group, census tract, and other variables to facilitate this process. So you'll see land use affects socio-demographics and economic indicators, and vice versa. That also works through the system. Once we did these models, we started building a simulation engine. Again, in the interest of time, I'll go into this one. So here we have a simulation engine where we are doing the land use models. Then these outputs from these models go as inputs into the economic and demographic modeling. They influence population, ethnicity, vehicle ownership, and so on. And then what we do is every year we aggregate all the data. Once we process the parcels, economics, and social demographics and variables, we take stock of what is going on for that year, take that, and then cycle that into the next year. So this is a process that is repeated yearly. So we started with 2020. Every year we repeat this process and go to the horizon year. So if we wanted to go up to 2050, so we ran it through 30 years, 30 cycles. So before we did the 30 cycles, we wanted to check. So we used 2019 data and the models we developed to predict 2020. So we are doing one cycle of data as a validation to see what we are predicting and how are things changing, but we compared it to the observed. So we know what 2020 really looks like. So we modeled changes. We changed the 2019 data with our models and saw how 2020 looked like. So you'll see that across the various land use types, we are doing a very good job. Again, there are differences, which is natural, but the differences are never very large. So this kind of gave us the confidence to go forward and build and run the algorithm moving forward. So here I'll show you the simulation results. So this is, again, we have a lot of data. So we are trying to show you some interesting trends here. Here, for all the land use types, I'm showing you the percentage of area changes at every time point. So we have 2020 to 2050 here. So you will see recreational, again, reduces a little bit. Single family residential keeps increasing. Again, not surprising given the population growth in Florida. There will be demand for more housing. You'll also see multifamily residential increasing. You'll see vacant commercial increasing. Agriculture drops. That is the most significant drop you will see across all land uses in terms of the percentage, which is, again, expected as more and more demand for space comes up. The lower income earning areas might change from agriculture to something else. So again, these are based on the trends that we have observed. So vacant residential also increases, commercial and different land use increases. So this is the overall summary at different time points of all land use types. So once we were able to generate all of this, we spent a good amount of time making sure these predictions follow reasonable expectations. So we checked it, we looked at how single family residential percentage is changing, how is multifamily percentage is changing, population and households are changing. So again, this is to ensure that we are going along expected trends. So as population increases, you want to make sure there is enough housing, employment should be adequate. So these things we wanted to check. So here are some percentage descriptions of the different jobs. You'll see the employment numbers are increasing reasonably over time. Look at the industrial. There was a dip in 2020, but it's recovering over the last few years, and it's expected to continue in terms of the commercial percentage. So these are again some examples illustrating that the data that we get are representing reasonable expectations of what we see going into the future. Same thing with the number of jobs and median income. Again, you will see the number of jobs increase steadily over time. The speed at which they increase slows down after 2035, but they keep increasing. Again, median income is on the rise as Florida gets more technical jobs. I think this is expected, and this is following expected trends. We also looked at some job per capita numbers. So again, we can't expect the number of jobs per capita to go to 1. It doesn't make sense. So here you'll see that it has stayed relatively stable from 2030 to 2050. Again, we're not over. The number of jobs are increasing because of population growth, not because suddenly everybody is working, which wouldn't make sense. So here, this is a good indication to see that while jobs are increasing, it represents a trend of because population is increasing and the number of people employed per capita per year remains the same. Another important aspect when you look at a simulation of this large scale is to consider the impact of randomness, right? Because when we run the entire software, there is a random seed that goes into the picture. So now if I change the random seed at a parcel level, the decisions will change. So some parcel we tag for a change in 2025. If you run the simulation again with a different random seed, it might not have that change, which is again understanding how simulation and Monte Carlo process work. That is reasonable, but that should not affect aggregate level results. If one parcel changing because of micro simulation changes the percentage of single family in a county, something is off. So what we did was we changed the random seeds and checked at each resolution how the outputs change. We are not focusing on a parcel. We are not saying, okay, what happens to this parcel under random seed 1, random seed 2. No, we are not looking at that, because that it can change. That is valid for one parcel to change into a different type. We are focusing on what is happening at the block group level, what is happening at the census tract level, and what is happening at the county level. So we'll show some results here. So this is a table where we're looking at the different land use types. We ran the software 3 times. The first run, second run, and third run are 3 types. So here I'll talk about agriculture. So in the first run, the percentage of agricultural land use was about 5%, 5.21% in the first run. What you'll notice is across the 3 runs, things change, right? It's not, obviously it's not exactly same, but what we get is well within an expectation range, right? So we're changing between 5.21 and 5.27. And also interestingly, if you look at the standard deviations, again, they're very close. So what this tells you is the distribution is different, because again, it's a random process at the end of the day with some behavior, but the mean and standard deviation of the distribution is very close, which gives us confidence that the random noise in the system is not affecting data at the block group level. Again, another variable, single family residential. Again, we're changing between 34.2 to 34.25. Again, same thing with the random standard deviations, very tight, very close. So it tells you that randomness is working exactly as it should. It's not creating any errors of that nature. We did the same thing at the census tract level, similar results here also. Same thing at the county level, again, very similar results. You'll see very stable across the run. So these are different randomness. So if you look at every parcel, things will be very different. But it's very encouraging to see that at higher aggregations, things remain stable, which is what we are expecting, which we are trying to aim for in a product like this. So with that, again, we were able to identify the outputs and that they make sense. And then we'll move into the actual data products. So what we wanted to do here was we wanted to provide all the data we generated in these 5-year increments in two forms. We wanted to give data in a CSV file and as a GIS file in a shape file. So we have GIS layers. We also have parcel level files. So for those interested, you could also reach out to the DOT and get those parcel level files and use it. Again, these are large files, and if you don't have the resources, you don't need to use those, but you can go into the aggregate files and get for your county, census tract, or block group. So we prepared these GIS layers from 2025 to 2050, and we created files for different spatial resolutions for aggregates and for in this fashion. So there is a 2025 block group file, 2025 county file, census tract file, and so on. So all of these are well labeled and created. There are different variables. Again, we'll show a little bit more. So from this, you could look at GIS layers like this. This is an example here. I'm showing things changing in Miami-Dade, for example, from 2020 to 2025. We can also look at how the block group population forecast looks in 2025 across the entire state of Florida. So because all the block group data is available, we're able to plot this at the block group resolution. Similarly, we can do median income at the census tract level. So again, these are just example files we created here. So now what I would like to do, again, we can take a break if there are any questions before we do some demonstration of the data. We'll be happy to answer them. If you have any questions, again, we have a small group of people, so we could mute yourself and ask us questions if you have any. If you don't have any questions, we will move to the demonstration site.
Yeah, Doctor, I don't see any comments in the chat section.
Yeah.
So yeah, let's. I guess if there are other questions, we can always utilize that function. So let's move on.
Yeah. Okay. So
Yep.
so I will stop sharing for a second.
Okay.
Lauren will give a demonstration of the data with at her side. So I made you a co-host, Lauren. You should be able to share.
Okay. Let's see. Okay. And everyone see the screen?
Yeah, it's not full screen yet. Yeah, we can see it. Perfect.
Okay, cool. Okay. So, hi, I'm Lauren Hoover. I am one of the PhD students who worked on this project, and I'm just going to show you the data that we produced. So, as Dr. Lura was saying, we have the data there are three kind of formats that the data is in. There's the original parcel file that we generated. That's the base file that has all of the as the original data. Then we do a GIS layer so that it can be visualized. And then we also aggregate at the block group, census, and county levels. So just to recap, we've got our GIS file, one for each county, and there are 67 counties, and then we've given years, 2025, 2030, 2035, 40, 2045, and 2050. So the GIS is broken down by county, whereas the parcels, we have them just all of the parcels in, and then aggregated at the block group. The parcel data file would look like. So it's a CSV file, so it can be opened in Excel. Every parcel, we have given it a unique ID as well as the original unique ID that the county had given it. But we created a new unique ID so that we could standardize it across counties. We've also got X and Y coordinates for where the parcel is located, the land use that this parcel has, the area, the block group ID, which is the lowest resolution, so that we can identify where it is located, and associate it with census variables. And then the rank. So the rank is identifying specifically for those cases where a parcel splits. So if a parcel splits, then it will have a rank 1 and a rank 2. So the split will, for example, if we have a commercial or an agricultural parcel that gets bought and only half of it gets used to change into residential, then the first half that's still agricultural will have a rank of 1. If the part that changes to residential will be rank 2. So that's the base parcel data. Now we've put it into GIS format. So all of that data that we just saw is available attached to a shape in GIS. So if we clicked on any of these shapes, we would be able to see that information associated with this parcel. And then this GIS file allows us to visualize the differences over time. And then we've got our aggregated data. So from our parcel data that we had, we aggregated it by block group, and then from block group to census tract, then census tract to county. So the base information that we have is what land use is. So we already had land use and area at the parcel level. We aggregated all of the parcels that were in a particular block group and figured out the area for each of the land uses. So we've got agricultural, vacant, commercial, industrial, additional, mixed use, multifamily, office, other residential, public, recreational, single family, and water. And then we've also got a land mix category to kind of show how diverse the land uses are in a particular area. So this data is available at all levels. And then the variables I'm going to show you are available at higher resolutions. So for example, now we've got land use at all levels. Now we have our block group data, the socio-demographic data that was available at block group level is population and racial distribution. So we have that at each of the block group levels, and then we aggregate it so that it's also available at the census tract and at the county level. So then at the census tract level, we have household density, vehicle availability, and then income. So these are all available just at the census tract, or they were not available at the block group level. So just census tract and county. And then finally at just the county level, we've got jobs, job density, businesses, and business density. And then also job percentage by industry, but there were a lot of those, so I did not include a screenshot of that. So now that's a lot of information that we have. How can we use it? So one of the major intentions of this project was for it to be integrated into travel demand models. So we wanted it to provide data, and that's what the survey was for, was to provide us with information on what data is used in travel demand models. So I'm just going to walk you through. So we have it at so many different spatial resolutions, it can be used at any level. And we have included variables that are often used, like income, population, vehicle ownership, employment. So I'm going to walk you through the urbanized area transportation for trip production rates. So just how many generated in a block group for 2045. So this is for home-based work trips. The variables that are used here are number of automobiles, dwelling unit type, and number of persons in a household. So I'm just going to kind of walk you through how we would use our data with this model to kind of make it all, or to predict trip rates. So we're looking at the top the top census tract in this list, which just is conveniently in the middle of downtown Gainesville. So this model was produced for a parcel like that, or an area like this. So we need, for this model, we need to know number of dwelling units by type, number of automobiles available, and average persons per dwelling unit. And we're going to use, so here's a subset of our 2045 projected data, the things that we could actually probably use. I didn't really take a screenshot of all of it because there's a lot there. But these are the pieces that we can kind of use to get the data we need. So for a number of automobiles available, we don't have to do anything. It's already there. We've already got number or proportions by household. So 4% of households have 38.9 have 1, 41 has 2, and so on. So moving on to average persons per dwelling unit. This one's going to take a little more math. The long-range transportation plan that was developed already included this table for us to use. So we just need to know how many average persons per dwelling unit. So that's just going to be population divided by our household. We've got 2.68. And so again, these are how we can use this data that we've produced to input into models that already exist to kind of produce the data that we want, or to kind of learn what we need. So finally, number of dwelling units by type. We've got, this one's going to take a little more work because one thing that we did need to research for this, or look up for this one, was go back to the census and look up, okay, how many units in 2020 were there of multifamily and single family. Then we can use the 2020 base year data to determine the area in this census tract for how many acres are dedicated to multifamily and single family housing. And from that, we can get our units per area and then using the 2045 data, we can get the area in the future and then from there we can get units, or calculate based on area and units per area, how many units, and then adjust for the actual household size or the number of households that are projected to get our new number of units and the proportion. So these are just some ways that you can use our data in this model to get trip generation rates. So you can see here all the proportions for all 165 households to get your trip generation. So that was one case, probably the most common case, but some other things that we're hoping this data can be used for is directly observing projected changes. So we're looking at that same area, just a few interesting variables looking at population. You can see that it's increasing from 2025 to 2050. Households as well. Income is as well. The multifamily and single family housing is decreasing, especially single family, which is indicating to us that it's kind of probably it's heading towards densification. It's going to be a more densely populated area than it currently is. So things that you can look at in your area if you want to see what projections are for the future. And then finally, looking visually at land use patterns. So you see over here, for example, Miami-Dade changes, or in the northwestern corner, it goes from mostly other to, or almost entirely other to, it has a few interspersed agricultural parcels. So just different things that allow that you can use this GIS data to visually analyze how land use will change over time. So that's more or less what I've got. And so I'm going to hand it back to Dr. Luru.
Thank you, Lauren. So let me get back. Okay. Thanks, Lauren. So again, what Lauren presented was demonstration of how you can use the data sources that we are generating. There are other use cases, right? So for example, you can look at different regions, how they are changing. You can look at if you're a urban region or a small town that is growing rapidly, you can see where you're going to be in 2030, where you're going to be in 2040, and plan proactively. So by observing the changes, you can say, okay, this region, this data set provides information that potentially we are a fast growing region. So how do we adapt for that? So what can happen? Where are the new single housing units going to come? How do we proactively plan transportation infrastructure for? So this can be very helpful for rapidly growing locations. And then so that they know where they are going to be maybe in 5 years and 10 years. And again, they can always come back and check those numbers as they go forward. But that, I think, is a very useful tool for the agencies that they don't have the resources to build it, but now we have already built it and they can use it. So in terms of quick takeaways, again, we developed a standard system across the entire state, providing very high resolution estimates of land use, socioeconomic and socio-demographics and economic indicators. This is all developed through an open source software, and all the data are available with DOT. And again, I think Thomas and his team will decide how they want to probably allow usage to other jurisdictions, but we'll be happy to help any users with any questions or any potential use cases that can be identified. As I said, we think that there are unlimited number of applications for this data. You can use it in travel demand model as we showed, but you can also look at trend analysis of understanding what is happening with your jurisdiction. You can also start looking at safety issues, right? So you can use this data to see where you are on the safety curve. If you look at some of the regions in Florida, there are what land use patterns are highly correlated with higher number of crashes. So every jurisdiction goes through a phase where it starts growing, crashes happen, and then we figure out strategies to reactively reduce those crashes. But now if we have a image of 20 years into the future or 25 years into the future for each jurisdiction, so each jurisdiction can say, okay, we are in the slow growth phase, but in 10 years, we'll start growing fast. So how can we proactively address safety problems even before they happen? So when we are building the roads, what have other cities done reactively that we can plan and implement proactively so that we don't have to go through the same cycle of high crashes that happened in different other neighborhoods. So things like that, I think the data sets that are generated will offer useful insights. And I think it's up to the creativity of the jurisdictions that they can use this for different sources. We have come up with 4 or 5 use cases based on what we have thought, based on what our experience is. But we think putting the data out there will create more discussion and more use case analysis, hopefully, in the future. Again, the data has been submitted to the DOT. We are waiting to finalize the full project and then address the data availability. Okay. So there are some questions on chat. I'll get to that. But again, Thomas or anybody else, if you have any questions, feel free to reach out. You can unmute and ask me. Okay. So I'll answer the question on chat. Do you have a simple list of land use attributes? Yeah. We have land use attributes such as area of the parcel. We have the type, land use type for that, and the geocoded location, and these are available for every 5 years. We have this information. We have yeah. Is that what you're asking, Rob? I don't know if I'm getting your question correctly.
Sorry, I'm multitasking.
Sure.
Yeah, I was wondering what
Yes.
are all of the attributes that you have,
We have
as
the area
well
of the
as
parcel.
what
We have the
years are available.
Yes.
Sorry.
Yeah, so we have the area of the parcel, because once you have we have the type of parcel that it is. So if it's a business, a retail parcel, or a single family parcel, we have that information, and we have this every 5 years. Yeah.
So all of that is in acres?
Yes, the parcel area is in acres. Yes.
Okay.
So the question by Wei, do you have a way to adjust the forecast results when local information doesn't match? Okay. So right now, because we don't have that information, we don't have it, but there should be it could be a simple way to change that. We can update the independent variables at some point. We might have to rerun the model, or look at a quick way to scale it up, because if we know the project, so let's say the project is a single family residential unit. Let's say they're building 1,000 new homes. Now that would alter the land use of that region significantly. So I wouldn't suggest using a simple scale approach, or simply dividing by a fraction, or a adjustment amount. There might be a need to run the model using those inputs from that year going forward, because some of these changes could have a very non-linear effect. But yeah, that would be something to check. It would and a more appropriate way would be every 5 years we use new parcels data, and then recalibrate it quickly. That would be helpful. That would be the most efficient way. But there could be other ways to adjust for these trends going forward. But the data directly won't do it. We will have to work with the DOT to figure out an adjustment approach if we want to do that. I hope that answers your question to some extent.
Dr. Eluro, can you hear me?
Yes.
This is Cesar Segovia. I was wondering the interaction between, I don't know, maybe I missed that part. And I'm sorry, I'm on the road right now. I'm not driving, but my signal may be weaker at some point. The interaction between transportation and land use. We know that when you build a new alignment, a new interchange, the development focus on that new interchange, around that interchange, how you can introduce that factor into from that year that the interchange is open moving forward. Is there a way to do that?
Yeah, so we thought about this aspect. The challenge with doing that is we will have to predict where transportation infrastructure is going to be put into the future, right? So we do not have information on where transportation infrastructure is going to go. So we decided to represent that through jobs, through population change, through density. So those aspects are where we are not projecting the transportation network into the future. We are not doing that, because that would again create significant challenges on, we have to decide where we'll put lane expansion, where we'll put interchanges. I think that will make the project even significantly harder to implement in a 30-year time frame. Maybe for 5 years we can do that, 10 years we can do that. Beyond that, I mean, are we predicting transportation infrastructure correctly becomes a challenge. So we decided to not get into transportation of that detail, right? So we are looking at how people move, how employment changes, and that to represent impact on land use patterns. Again, it's a very valid point. What you're suggesting would be nice, but I think it complicates the overall process for a 30-year horizon substantially. So we decided not to go that route.
Right. I guess we do at least a free flow from the base year and apply it to some measure of the scheming of the accessibility of the undeveloped land to be more attractive to future development, for example. So that would be a nice
Yes. So we capture
the model.
We capture that by looking at, for each parcel, we are looking at what is around it at a certain distance. So we are looking at and we're also looking at what changed. So if one parcel within that, more parcels within that census tract are changing in the last year, we have a variable that triggers increased change, right? So, or it stops after a point because there's only so much land you can change. So if we see that things in the vicinity are changing because there is a single family development came in 2021. So in 2022, that will trigger more single family changes potentially. So that is how we have used these variables, so that nonlinear relationship of jumping off of some change can impact the process. So that is, I would say, considered. How much available land is there, how much vacant residential is there. These are variables we tried in our models when we are looking at the land use change choice. So if they are significant, they will influence that process going forward.
Great, thank you.
Okay. But again, great points, and we agree. There are some. We are not saying there are no limitations for our project. There are significant aspects. So again, along the same lines, we don't have data on local planning guidelines, right? So we are not trying to consider. This is not a specific jurisdiction-based project. We are not trying to do a land use planning for Miami-Dade County, or we are doing it for the entire state. So it definitely can be improved if you want a jurisdiction-specific model, right? So we can always recalibrate the models for a jurisdiction, but this is a starting point from where these discussions can go forward. That is our intent for this project. So we did not have the data on max development capacity for the entire state. So we could not consider that. So, but if the data is available, we could incorporate it as needed, but we do not have access to that data. I'm responding to please.
Yeah. That would be the other question I had in terms of local policies and urban growth boundaries and all of these. There's a maximum density, that jurisdiction over there. Don't want to go over that, and when it gets to that capacity, you have to move on to a vacant line or extend the urban growth boundary. It will be some utilization of the mall to have that possibility there.
Yeah. No. Yeah, go ahead, Tom.
I think the floor area ratio, like the maximum density, can be controlled by the user, but the model's telling you is where particular use wants to go, and you can make some decisions and flexibility about how much of that development actually occurs.
Right, I was thinking in terms of the future land use maps that the local jurisdictions have, and of course it's a very complicated process because every jurisdiction have different designations for their future land use. So you have to normalize all of that first before you can actually apply. And these are all GIS layers that you can put on top of the census tracts or the parts of the level data that you have. And from there, you can apply this as a limitation. But you can increase the sophistication and requirements of the forecast going to the future by applying that. But yes, it will increase the complexity of the model.
Yeah. Again, we are very happy to work with any jurisdiction to update it based on, but that data has to be available. If the jurisdiction has that data and requirements, then we can. I think it would be a reasonably simple exercise to do it, but we could not do this for the entire state at this point. Yeah. So Walter has a question on. So yes, so there is population estimate. So we used 10 years of data, right? So we have data from 2010 to 2020 to understand how things changed across all the variables. So there is a pattern that we extracted in our model development, which also includes some information on future population that served as a control. So the growth that happened that was observed from 2010, 2011 to 2020 was incorporated into our models, and that was evolved into the future. So that's where the growth patterns change. So when parcels change, they're usually changing from agriculture to other. So those patterns are extracted from data. So this is data-driven forecast, growth forecast, but we did not want to project 30% increase in population or anything ridiculous like that. So we have controls that come from future population estimates that are used to make sure we are within a band. We are not overestimating the growth. Okay, thank you, Walter. Are there any other questions?
I guess if nobody is asking any questions, can I add one more?
Please.
I like the fact that you have different systems in there. For every land use, you have a different, consider like a different system, and that is a good thing. What I'm trying to figure out is, did you consider any other model that you are using? Multinomial logic model. Did you consider any other models to come up with the forecast or the estimation of a different model? This was the mostly widely used everywhere, and you decided just follow with the multinomial logic.
Yeah, so the model was used as a way to represent the choice, right? So we decided on the conceptual framework. So there are land use models, like there is urban sim and other kind of systems where they model land use pattern evolution in a different way. So we said we wanted to model it at a parcel resolution, every parcel, how they will change. So once the conceptual framework of how we are modeling each parcel, how it will change. So once you have that, there's only two choices. The parcel either will change next year or not. That's a logistic regression. I mean, you can do machine learning, you can do anything you want, but the choice there is, will it change or not? So the conceptual framework governed all of that. Now, there are different ways of doing it. You can start saying, okay, why do you need to worry about every year? You can look at longer time frame, so maybe every 4 or 5 years. Again, that's something we could discuss, and there could be different ways. But once we settled on a framework to process the data, and given we have 10 years of data, we wanted to have 10 chances to model change. So that would give us enough patterns in our model system to predict it into the future. So that's our thought process, I would say. Okay, so there's a question here. Do you account for the difference between areas with sufficient vacant land to accommodate future growth? And yeah, yes. So we keep track of percentage of land in different land uses as we go forward in the future. So those are variables that affect. So if percentage of vacant land influenced single family development in our models, it would influence it in the future also. Again, percentage of vacant land might not influence some land use types. So we tested it in every model. Whichever model that variable had an impact, we retained it. So we tried different combinations. So more single family might lead to more single family, or after a point, more single family might lead to no more single family. So we tried different combinations of these variables, and each model system is a little different. So we tested for this. I cannot say where vacant land is significant. I'll have to look at the number specifically, but we tested for this possibility. Again, as you're thinking of questions, I just would like to acknowledge my team, Sudipta, Lauren, Istiak, Divan, and Shusmita. They all have worked on this, and Sudipta was the one who led the project. Of course, he's now employed somewhere else. But yeah, again, this was a huge effort in terms of team members. And again, we also had a regular advisory meetings with Thomas, Vladimir, and Terry, with help from Sheldon from Cambridge Systematics and Krishnan Viswanathan. So again, all their feedback and thoughts from them, we tried as best as we can to incorporate them, but we would like to just thank all of them for their inputs.
Thanks for your time today and your staff's time on all this. I mean, this was a really good project. You guys did lots of really great work, and I think there's a lot of potential for using this across the state. I'm very excited about where this can go.
Yeah, thanks Thomas for all the support. I think it's it was very well-intentioned support, and we really appreciate that.
Are there any other questions? Any thoughts or comments?
Where can we locate the data?
We will put this out on the hub. And we're still checking off a few things just internally in operations, making sure that we can answer the questions. And but our goal is to get this out there with all our other model downloads. Same page.
Hopefully there'll be some sort of announcement when that is
Absolutely.
available.
Yeah,
Okay,
absolutely.
great.
No other questions. Dr. Liu, your team, thank you so much for your time. Yeah, look forward to moving with this.
Okay, thank you so much. Thank you
All right.
everybody for attending, and we appreciate all of your time. Thanks Thomas and Vladimir, and we appreciate it. So take care. I'll stop the recording and I'll close it. Okay, thank you.
Very good.
Thank you.
Bye.
Thank you.
Bye.
Thank you very
Thanks,
much.
everybody.
Very informative.
Thank you.
Bye.